Okay, double integral. So let's start from single variable integral first. So if you have single variable function, okay, maybe this is the function f of x here. What I need to go through is, what does the integral means first, okay? Yeah. When you do integral, basically the idea is to approximate the integral or the area underneath this curve using a series of or addition of a series of these rectangles that are here, right? Yeah. So if this is x of k minus 1, and if this is x of k at here, okay, then for this rectangle, that we know that the area for this rectangle is what is basically the base area times the height. Okay, and the base area is a delta x k. Okay, suppose this is delta x k here. Okay, and the height is f of x of k minus 1, for example. Okay, like this. Okay, so then for this rectangle area, the area, so let's call this is a delta s, and delta s is f of x of k minus 1 times delta x of k, right? That's the area for this one here. Then the total area is addition of all of the rectangular area here. So the total is approximately, basically, the total area underneath the curve. The total area underneath the curve is approximately addition. Okay, how many are we adding? Maybe we're adding from 1 to n, adding all of them together. So that's integral, approximating. That's basically what the basic concept in numerical analysis. You use, you use a small quantity and then you put them together as an approximation of an exact solution, basically. Okay. So then when n approach to infinite, then that total, this is not approximation anymore. If n approach to infinite, then it becomes the exact number here. So basically the summation sign becomes an integral. So we're probably integrating from a to b. So this is probably a, and this is probably b, a to b like this. Okay. And what are we integrating? We're integrating f of x and dx like this. So basically, this is how integral is conducted, right? Okay, yeah. So in other words, okay, as you're going from a to b, as you look at this one here, as n becomes infinite, so you are essentially sweeping through a to b. Okay, so sweeping all the way through a to b, the range, right? But not redundant, just once. Okay, between a and b, the integral meaning you sweep through a to b just once, cover all the possible locations between a and b. Okay, that's the integral. That's a single variable integral. Okay. So now comes this double integral. Basically, when we have a function of two variables. So let me formulate the problem first, and then we go from there, right? So let's just think about the following problem here. Let's say I have a function of two variable given z equal to f of xy here. So we know this is a surface, right? Maybe this is a surface looking like this here in the 3D space. Okay. Now the question is, the problem I'm asking here is, what will be the volume? Okay, what will be the volume between this surface and its projection in the xy plane? So projection, basically, you project this surface into xy plane. See, okay, project it into xy plane. Let's just say maybe it's a shape like this. So when you're looking from the top, right, and that's the projection of the surface. Then what we're interested in is this. What's the volume between the projection and the top of which is covered by the surface z equal to f of x, y? And of course, you do have probably a certain kind of you know sidings like this, right? Yeah. So the problem here is what's the volume between z equal to f of x, y, okay, and its projection in xy plane. So sometimes when I say its projection xy plane, I will say that in a different, very simple word is what's the shadow, okay? The shadow of f of xy, okay, in xy plane. So that's basically the formulation of the problem here. It's actually pretty much same like this formulation, basically saying here's a function, what's the area underneath the function, right? That's the integral, okay? So I'm giving this problem here. Okay, so if we have this formulation in the problem now, and we're trying to use a similar idea as the approximation approach to find this volume, so what do? We can do this. Let's find a very small area inside this projection, okay, or inside this shadow. Okay, so let's say this is a rectangular area, very small though, huh? Very small. So the area is probably centered, okay, around, let's say, x of k, y of k. So the center of this area is here, okay, x of k, y of k. So basically, it's more of this. This is x of k, y of k, and then you have a delta x and delta y like this on the two sides of this small area. Okay, yeah. So then, if you extend that rectangular small area up, okay, extend it up, and you know that they're gonna basically intersect the surface at a certain point, right? You know, you go up and then it'll touch that roof, the ceiling. And the bottom line is, you will have some kind of not a cube, some kind of a rectangular box over here, right? You can approximate it as some kind of a rectangular box here. So the simple idea is, what's the volume of this rectangular box, right? This box here, okay? So the box, right? The volume of this box, okay? The volume of the box is the base area times the height, okay? So base area is this area. So the base area is delta x, delta y, times the height. Now, because this is imagine this, right? This is a very small area, very small, very, very small. So I can approximate the height using what? Using f of x of k, y of k here, right? So that's the height. Okay, yeah. So this is the volume of the one particular box, very, very small box. And we're looking for is actually what? We're looking for is, imagine there are number of this rectangular area inside this shadow. So you can construct similar boxes just like this one. And then you add them up. That'll be an approximation of this volume here, right? Yeah. So basically, what we're trying to do is the total volume is approximately summation of let's just say you have n number of boxes, and each one of the boxes can be expressed using this function, this expression here. Okay, yeah. So you sum them all up, and you get approximated volume, okay, between this top surface and the bottom shadow, right? Yeah. Okay. So same idea. If I extend this n to infinite, then that summation will become integral, right? Will become integral. So in this particular case, right, when n is approaching to infinite, basically delta x goes to 0, or in other words, okay, delta x becomes dx, and delta y becomes what? dy, right? Very small ones there. Okay, yeah. So that total volume that the problem formulated that we're looking for, okay, the total volume is equal to basically two integrals. So you see, because there are two variables here. And what are we integrating? We're integrating the function f of x here. So dx and dy. Okay? So that's the integral, see, basically where double integral is from. Okay. Now, if I go back to the simple case for a single variable, you got to put a range here, right? We're integrating for x, a to b, right? Yeah. So now this time, you're integrating, it's not just simple from a to b. You're actually, integrating over where? Inside the shadow here, right? So basically, you're moving the box everywhere in the box, in this shadow, trying to fill up this shadow area here by as many boxes as possible. Okay? So in other words, what the integration here, it's not going to, you're still going to have an integral limits, but now we don't know what the limits is. I want a general expression. So what I need is, all I need is double integral, right? I'll just use the r at here to indicate that this is my shadow region. Okay? So r basically here is defined as, okay, the region, okay, where z equal to f of xy is defined. Okay, that's the r. Simply put it, r represents the shadow. Okay, yeah. Okay, yeah. So single integral, you want to integrate from a to b. In other words, you want to sweep from a to b without redundancy. Okay, you don't sweep to a to 3 and then go back to 2, and then from 2 to 3 to b. No, you don't do that, right? All the way, just once. Now this time, this integral meaning is you want to sweep through this region R, right? Sweep through region R, and without redundancy. So basically, you need to basically find all the possible locations in R, but you don't do it. You don't go through the same location twice. Okay. Okay. So now here's the definition. All right. The whole question next is, what do we do? How do we calculate this thing here? Okay. If I look at this, the way that we do the approximation, if I calculate like this, I need to find as many boxes as possible, then let n equal to infinite. Just think about the process. It's a headache. Okay, it's not a very intuitive way of doing it. But the one that I just said, that sweeping, that idea of sweeping, is actually the guideline that we're going to do here. Okay, so we're still going to use the approximation idea here. Okay, so let me do the next one here. So how do we calculate a better way of computing this double integral? Okay, yeah. So to calculate this one here is, so this is my tools to illustrate the idea here. So this is the surface. Okay, this is a loaf of bread. If I ask you is, what's the volume of this loaf of bread? Right? Okay, so you put the loaf of bread here. Yeah. Oh, I forgot to. Oh, that's good. So this is the surface. Which is what? Z equal to f of xy, right? And what's the projection in this? Here's a projection. So it's a pretty beautiful surface because you have a fairly clean cut, right, on the four sides here. Of course, in the reality, you probably have some bumps in here and that. Okay, yeah. But in terms of this, so tell me, how do you get the volume then? Can you just think about it, just a very intuitive way of getting the volume? Every slices, and then what? You add them together, right? So that's a pretty intuitive. You have one slice here. If I can find the volume one slice, then you add all the slices up, right? So that's basically one way of doing it. So now let's use this idea here to get certain formulas. Okay. It's my dinner. No butter. Okay, so I'm gonna draw something like this loaf of bread here. Okay, yeah. This is about the top surface. Let's say this is my top surface here. And it's going to be projected to the xy plane. Okay, yeah. Okay, so the top surface is z equal to f of xy. Okay, so we're going to slice this bread. So we're going to do a cut. So we cut it, let's say anywhere. So we choose in the middle of somewhere here. So we're going to cut it. Probably, let's see, at this location. Okay, so for that one particular cut, okay, so you have a intersection like this. You have a cross section like that. Okay, yeah. And that one particular cut, maybe for that one piece, maybe there is a very thin slice, so there is a thickness of bread. Okay, thickness bread like this here, right? Yeah, it's pretty small, huh? It's pretty small. So if it's a pretty small slice, then the approximation idea is what? You can consider the two cross sections adjacent to each other, this side and this side, to be the same thing. Okay, if it's a small cut. So if I look at this cross section here, okay, if I look at this cross section, so what does the cross section look like? Okay, so that cross section will look like more or less like this. So basically, this is y, this is x, and this is z. So I'm going to look at this cross section in this particular case to make it easier. I'm going to look at it in the z-y plane, okay, in the z-y plane here. So that cross section, maybe it's like this, okay, it's like this. Okay. And where is the cross section being cut? It's cut at an x location, okay, at the arbitrary x location. Okay, yeah. So for the top curve, okay, for the top curve, where is the top curve from? It's still, the top curve is at a certain value of x. So basically, it's f of xy. Maybe it's f of 3y. Maybe it's f of 2y. Who knows, right? So I'm going to keep general the x value. Okay, yeah. Is that clear? And for this cross section here, what you also have here is you have this value, which is, let's call it mean value, and this value, let me call it a max value. Okay, so for that cross section, you have a minimum y value, you have a minimum, you have a maximum y value, right? So now I'm ready to do the approximation now, right? For this one cross section, what's the area of one cross section? So for given this cross section here, the area is what? So basically, that's the area of one slice, right? That's the area of one slice, one general slice. And this one slice, the area equal to, it's basically the area underneath this curve. You're integrating between y mean and y max, okay? And the integrand is this function here, right? So dy. Okay, so you're integrating with respect to y though, huh? Yeah. So guess what? When you're integrating with y, what do you do with x? You treat x as if it is a constant, right? Yeah. So that's area of one slice. That's area of one slice. Then the volume of this one slice, as we do this approximation. So suppose that this bottom here is delta x. Okay, so delta x here. So volume of one slice, okay, is this area times the delta x, right? This area times delta x. So it's basically that area times delta x. Okay, so it's volume one slice. And what we need is, we might have 10 slices or 100 slices, who knows, right? So what we need is to add all the numbers of the slices together as approximation of the volume. So the total volume, okay, is addition of volume of all slices. Okay? So basically you're adding this thing, right? Adding this thing by how many times? By n times, let's say. Okay? By n times. Okay? And that's the approximation. And then you let n go to infinite, right? You let n go to infinite. So this time it's not approximation anymore. That becomes the total, the exact calculation of the total volume. So now the total volume, okay, equal this n goes to infinite, which means this delta x will become dx, right? So as n goes to infinite, the delta x becomes dx, okay? And the summation at here becomes another integral, and this becomes another integral here. So this integral is the integral corresponding to this delta x, right? According to delta x, okay? So this integral delta x, basically, you're moving this slice, you know, from the beginning to the end. So essentially, you're gonna move like from, like maybe this is x mean, and maybe this is x max, right? So you're moving from x mean to x max. So your integral basically here is x mean to x max. Okay? In the middle, it's again, it's that portion over here. So y mean, y max, and f of x, y, and dx. Okay? There we go. So that's the total volume for the double integral at here. Was that good? Yeah. So the bottom line here now, if you look at this one here, it's the what would be the physical meaning of this y mean y max and x mean x max? Okay, so that's where you need to be very careful here. Okay, so keep this question here. So what are y mean, y max, x mean, and x max? Okay, so keep this question, and we'll look at this again in examples here. But bottom line here is we are slicing this bread, okay, or the volume or the object, okay, using a plane. In this case here, using the plane, actually the plane is parallel to which axis? To YZ axis here, right? But we're doing the cutting is arbitrary cut. You see what I'm saying, right? You're doing the arbitrary cut between the two edges. So when you do the cutting, for one cut, you find a mean and a max, right? If you cut it somewhere else, guess what? That mean and a max probably will change, right? Probably change. However, the next one, x mean, x max, what's the physical meaning of these two? It's what? It's from this edge to this edge, right? You know, moving from the slice at the end to the slice at the other end. So this x mean, this x max, they are not variables. They are actually constants, right? They're the constant referring to the edges of this region in the x-axis. Maybe there is a bump here, maybe there's a bump here, but either way, you need to find the two edges, okay, as the x mean and x max, okay? So this is basically, you've got to be careful right here when you find this, when you're trying to find these limits to do the integral, because all you need is to figure out the proper limits at here. If you figure it out, then you see that it's basically those two integrals, right? Yeah. So in my case, this one here, I will say not necessarily constant. Okay, and these two will be constants. Okay. However, you still got to be careful though, because you know I'm slicing this right using a plane parallel to the ZY axis. So what if somebody's saying is, can I cut the bread, you know, this direction, using the plane parallel to the ZX axis, basically cutting like this, right? So in that particular case, then your integral, guess what? Instead of this is y mean, x mean, all you needed to do what? to swap, right? However, then the x min in that case will not necessarily be constant, but then the y min y max in that case will be constant. Does that make sense? Yeah. So here's my first heads up here. The so-called order of integration, okay, matters. Okay, the order of integration matters, even though the end results shouldn't change. Matters basically means sometimes when you integrate with respect to x first, it's easier than to integrate with respect to y first. Yeah.
Should the inside integral be dy? Dx, dx?
Oh, yes. This is dy. Good. Thank you. Yeah. Okay. Yeah. Okay. So let's take a look at example now. Okay. And then we'll do a little bit more general summaries. So giving a plane z equal to 4 minus x minus y. So this is essentially your f of x, y at here, the surface. Okay, that's a plane. Can you find basically the volume? If I draw it out, here is the plane. Okay, find the volume between this plane, okay, and a region R, and region R is defined by x between 0 and 2, y is between 0 and 1. Okay, yeah. So let's draw the region R first. X between 0 and 2, y between 0 and 1. So it's a rectangle. Okay, so this is R here. Okay, this is R. And you have a plane on the top of this region R. So the plane is an infinite plane. But we're only looking for the volume between this region R and the plane. So basically, you're looking for is just extend it up until you reach that plane. The plane more or less look like this. Okay, so the plane more or less look like this. Okay. Okay. So what's the volume between the plane and the bottom region R here? Okay. Okay. Now, before you do double integral, your first step, as we're going to summarize, your first step is always to determine the order of integration. So which variable you wanted to integrate with? Do you want to get y or x first, right? So in this particular case, this is the simplest kind of a double integral you've ever seen. It really doesn't matter which variable you're going to integrate with. Okay? Yeah. So in this case, let's say I'm going to integrate with respect to y first, and then the x. Okay, so essentially, I'm going to apply this formula here. Okay, apply this formula. So if I apply this formula here, okay, so in this particular case, the volume equal to double integral R and f of x, y, and then this dA. So the dA essentially is a dx dy, right? So the small area. Dx dy. But you wanted to integrate with respect to y first. So the next step, when you write, basically you write two integrals here. Okay. We're integrating this function. The function is 4 minus x minus y. We want to integrate with respect to y first, and then x. Right. So that's what the template, right, for this order of integration. And after this, you need to figure out the limits now. What's the limit for y and what's the limit for x? Okay, for x. Because this is the simplest case at here. When you're integrating with respect to y, like the loaf of bread, which means what? You're going to cut that object using the plane parallel to which one? To the zy plane, right? To zy plane. So then guess what? If you cut it, parallel to that zy. Okay, if you cut it, it doesn't matter where you cut it. The y min, y max is always between where? Between here and here, right? So which is actually 0 to 1. So basically, your y min, I'll write it one more thing here for time being. So your y min is 0, and your y max is 1. Okay, yeah. And then dx, the limits for the x, essentially you move the plane. Okay, it's like you move the plane from one edge of this R to the other edge of this R. So you're moving from here to here, right? And that's x between 0 and 2. Okay? Yeah. So that's basically your x min is 0 and x max is 2. Yeah. So you see, back to the idea of sweeping idea. Sweeping. So what are we sweeping here? You do a cut, you end up with one line at here, right? Okay. Then you're sweeping the line from one edge to the other. Guess what? You are sweeping through this region R, right? Sweeping through the region R without any redundancy. Okay. See, that's the integral. So basically you're integrating over this region R everywhere inside R. Okay? Yeah. So once you get this now, it's pretty simple. When you integrate with this one first, treat the x as if it is a constant. So 0 to 2, that's outside here. For this integral, what do we get? We get 4y minus xy minus 1/2 y squared, and y goes from 0 to 1 like this. Okay. So sub this 1 here to y minus the other expression subbing the 0 over here. Yeah.
The first step, is it dx dy or dy dx? Above that. Step before that.
I'm selecting the orders to integrate the y first.
Yeah.
So that's why this is dy at here. Why is it dy? Because you see, you're cutting through that object using the plane parallel to the z-y axis, right? Yeah. It's a constant because of this particular selection of the region R. The min and the max are constant in this case, because it doesn't matter where you cut it, right? Yeah. It's always a 0, 1. You cut it here, 0, 1. You cut it there, 0, 1. Right? Yeah.
Right. Just the steps before that one. Is it okay, right? Dx dy, or should be right dy dx?
No, this is okay. At here, really, it doesn't matter.
Oh, okay.
Yeah. So you can write dy dx. That doesn't matter because you haven't started yet.
Okay.
Yeah. So dx times dy is basically the dA, the small area, right? It's considered the small rectangular area. Okay? Yeah. Very good. So 0 to, what do we get? We get 4 minus x minus 1/2 y and 1/2 dx, right? dx. Okay. And then another integral, 4x 1/2 x squared 1/2 x and 0 to 2. Okay? Is that right? Yeah. So sub this into here. You can simplify this. 4x minus this is a 7 over 2x. And subbing the x into it, you should get 5. Okay? Okay, so that's a simple example of a double integral. And that's the results based on the order of dy dx. Okay? And of course, you want to try, I think you should try, what would be the integration with respect to x first? Basically, instead of cutting like this, you cut it like this way, right? Cut it like this, okay? Yeah. You will get the same answer, of course, but try it out, okay? So here's my summary, okay? That's a pretty simple region R. It's simple because it's a rectangular region, essentially, right? But the region may not be rectangular. Maybe it's very arbitrary. Maybe it's a circle. Maybe it's actually, in later we'll see, maybe it's a combination of two different shapes. You know, it's a rectangular plus a half circle, something like this, right? Yeah. So we wanted to have a more general, basically, a case to deal with that. So let me do a little summary, okay, in terms of double integral, and what would be the proper way of doing it, okay? Yeah. Suppose that we are given f of x, y. So this is the integrand, okay? This is the integrand is given, and also a region R, okay? Region R here. So I will use is a more or less of a more sophisticated region R than the previous one here to illustrate the idea. So for example, okay, so this region R maybe is this. So x squared plus y squared equal to 1, and x plus 1 equal to 1. Okay? Yeah. So region R basically is bounded by two curves. Okay? So bounded by two curves. The first curve is a circle, and the second curve is a straight line. And x plus y equal to 1, and that's a line like this. So this is 1, this is 1, right? X squared plus y squared equal to 1. It passes through this point and passes through this point, and it has a part of the circular curve, okay, on this side here, right? Yeah, so the drawing is not very good, but that's the region. So what's the region R? So this is your region R, okay? That's bounded. And that's where the two things intersect, right? They don't intersect anywhere else anymore. Okay? So you have f of x, y. So imagine f of x, y is the thing standing on the top of where? On the xy plane, right? It's standing on the top of xy plane. Okay? And we're looking for the double integral. This double integral right here. Okay? Like this. Okay? So basically, what's the volume between that f of x, y and this region R right here? Okay? Okay, so this is what we do. Step number 1, okay, is to decide on the order of integration. Okay? Order of integration, basically, whether you want to integrate with respect to y first or integration with respect to x first. Okay? Yeah. So let's just say I'm gonna do this. So for example, I'm gonna do dy first, okay, and dx next. This is my current choice set here. Okay, dy first and dx next. So then the next step is this. Okay, next step. Next step, more precisely, thing is so there's a couple more steps involved in this one here, but overall, this is to find the y limits. Okay, to find the y limits. This is step number 2. To find the y limits, this is what you do. You're gonna draw this. Okay, you're gonna draw. There's the arrow. Draw here. Arrow, yeah. So you're going to draw an arrow lines, okay, in the y-axis, positive y-axis direction, anywhere between this region R or the shadow. Okay, so you draw one like this. Let's maybe choose a different color. So how do we choose the color? Red color, no? Pardon me? Oh, red color, no. Good. Okay, right? So you draw one like this. Okay, so this is the step here. So draw an arrow line, okay, through the region R, okay, in the direction of positive y-axis. Because we're integrating with the y first, that's why we do this, okay? That's why we do this. This is basically equivalent to the previous case. You're going to cut that object using the plane parallel to the z-y-axis, the plane, okay? Yeah. So when you cut it like this here, then what you do is imagine yourself there is a stick magnet here, so there's a guy, I'm always using this one here. Start to walk along this line now, okay? Start to walk along this line. Then this one will bump into, as you're walking, will bump into the region R at here. First contact, and then second contact. So first contact to enter, second contact to exit. And of course, maybe for some other complicated region, you might have a different thing. Then that's a different story. We're going to separate the region into simpler ones. So this is what we call a simple region, okay? Simple region. So first contact, second contact. Then the next thing here is, so y mean is the first contact. And y max, okay, is the second contact. Okay? Is that good? Yeah. Okay. So we know the wording now. Let's see, what will be the y mean and what will be the y max, right? First contact, what did it touch? It basically touched this x plus y equal to 1 straight line, right? And you want the y mean. So apparently this is not a constant. Because you've cut it to different locations, you get different values, right? But doesn't matter where you cut. The y value is always what? Y value is always equal to y minus x. Exactly. So this basically in this case, y mean equal to y minus x. Same thing for the y max. The second contact is on that circle. And it's a changing contact. Because you cut a different location, you get a different second contact value. It doesn't matter where, it's always on a circle. The value on the circle in terms of x is y equal to what? Exactly, right? Because this is in the first quadrant, so you don't need any negative sign here, it's positive. Okay? So there, that's your y mean, and that's your y max. And if you have a more other kind of a region, it's the same idea, okay? The same idea. So the first contact, the curve expressed in terms of x. Second contact, for the corresponding curve, expressed in the contact, okay? Okay, so that's step number 2. Then step number 3 is to find x limit. Okay, x limits. Okay. To find x limits, remember what happened in this case here. I said you sweep that cutting plane, right, from one edge to the other edge. Basically, imagine this is basically that arrow lines I just draw here. It's equivalent to say you sweep that arrow line, across what? The bottom region here, right? The shadow. So this is what happens here. So sweep the arrow line, okay, across the shadow. Or basically in here we're saying region R. Okay, sweep this R. Sweeping, you don't change the direction, just move it parallelly across this region R. So in my case, so what am I doing here? We are how do I select this in here? There we go. Yeah. So basically, we're going to sweep this thing right across this region R. Okay. So you sweep from this end to the other end and find the x mean value and x max value. Okay? So in this particular case, pretty simple. What's the x mean? 0 to 1, right? 0 to 1. So find x mean and x max that bounds, okay, the shadow. Okay, the bound shadow. The literally the edges. So in my case, x mean is 0 and x max is 1. Okay, yeah. So you see this way, what we're doing here is you cut it, you get something like this. Okay, you get something like this. Then you sweep it, you get this shadow, right? Yeah. As you're sweeping it, essentially you have the shadow. So you're going through, sweeping through all the whole shadow of the region. So essentially your integration over this region R, okay, without any redundancy. So the last step is, x mean is 0 to 1. Y max is 1 minus x to root 1 minus x squared. Then some kind of an integrand here, in dy first and dx next. Okay, so that's your last step, right? To put on the actual expression. Okay, yeah. So to do it quickly, exercise here. What if I decided to integrate with back to x first, then y, right? Then y. Can you write down the double integral with the proper limits? Okay. So what would be the double integral layout? Okay. Yeah, you do the same thing. You do the cutting. You do the sweeping. Okay. So now, because you're integrating to y x for x now, so what would be the first step? You draw a line in the positive x direction, right? Yeah. Find the first contact and the second contact. Then sweep that arrow line across the whole shadow. So, pretty simple. Okay. Does that make sense? Yeah. Okay. So no matter how complicated the region R is, okay, you just have to stick to this rule here. Okay, just stick to. And in the later part of the lecture, we will use a different coordinate system called a polar coordinate and something else. But no matter what, okay, it's the same idea. So let me give you an example without doing more of a calculation. Let's do it. This is pretty simple stuff, so I think we don't need to dwell on this for too long. Okay, so here is a double integral: 0 to x squared 2x 4x plus 2 dy dx. Okay, so here's f. Here's a double integral. First step, before you do this double integral, I think if you're giving the double integral, it's not that difficult to do it, because all you need is to start integration, right? For the inner circle first, and then do the outer loop there. Okay. But one of the skill you need to have is, well, can you draw this? Can you sketch this region R, or the shadow, based on this layout of this double integral here? So basically, sketch this R, okay, the region R, based on the layout. So the sketch essentially is based on the limits, and also based on the idea that we just illustrated. The idea is, what's the, here, first of all, you see which variable you're integrating with respect to y here, right? then technically you're drawing an airline in the positive y-axis. Then you sweep the line across the shadow to find x min and x max. So in this particular case, basically when you draw the airline in the positive y-axis, the line first bump into what? This, right? First bump into this. And then the second contact of the airline is this. Okay? So what you need to draw is, you need to draw this curve, and you need to draw this curve. So y equal to x squared is the first contact. So what is y equal to x squared? It's something like this, right? It's a parabola type of a curve like this, quadratic. The second is y equal to 2x. So 2x is like this, right? Yeah. So you can draw, if you want, you can draw them all out, so that's okay. Yeah. So that makes sense. So that's y equal to x squared. This is y equal to 2x. Then you sweep this line across this supposed shadow, and you get the limits 0 to 2. Now 0 happens to be the intersection of the two curves, that's fine. That 2, so the question is that 2 going to be the intersection between the two curves, right? And you will see that if you solve these two together, you'll see that that is 2 here, right? That is 2 here. So basically the region R you're looking at is this, okay? Is this. So I'm not going to do this double integral. Then the next question is, can you put down the layout of this double integral if you do the integration with respect to x first and then y? Okay, so what will be the limits here? Okay, what will be the limits? Because the integration is, there's nothing new regarding the integration there. Right? Yeah. Okay, so a couple 1 minute, you think you should be able to figure out the limits. Okay. So what do you end up with? What's the y limit? What's the limit for the x here? Y over 2 to? Sorry? Yeah, square root of, that's right, yeah. And the y will be 0 to what? 4, that's right. So if you do this, first contact, second contact. So first contact is y equal to 2x. And this, or in other words, is x equal to y over 2. Second contact over here, x equal to root y. And from here to here, so that value, if this is 2, and that value is 4. Okay, that's good. Okay, all right, so this is basically, that's it. That's basically double integral in Cartesian coordinates. Cartesian coordinates in terms of, it's basically it's x and y. Okay, yeah. So I will just write it on here. Okay. What we have just done is double integral in Cartesian coordinates. Okay. So you must be wondering, oh, okay, so there must be double integral in some other coordinates, right? Yes, there is double integral in polar coordinates. Before we move to polar coordinates, I want to show you an example. And basically, we'll see the advantage between when you evaluate the double integral using a different coordinate system. Okay? Yeah, so let's take a look at the example here. Z equal to f of x y equal to y squared. Okay, so here's my function. And the region R is x squared plus y squared, okay, less than 1, x greater than 0, y greater and equal to 0. Okay? Can you evaluate this double integral, okay, over this region R? Okay? Okay, so first, normally this is where things comes in handy is the question not necessarily always give you a sketch of the region R. So it's actually quite intuitive if you are able to sketch the region R out, okay, because that'll help you a lot in terms of finding the proper limits for the integrals. And this is pretty simple. X squared plus y squared less and equal to 1. What does that mean? That means what? It's inside a unit circle, right? And including the edge. At the same time, x and y are greater and equal to 0. So basically we're looking at is a quarter circle in the first quarter, basically, the first quadrant. Okay? That's your R. Once we get R now, we can start to do the integral. So let's now, we haven't learned polar coordinates. Let's integrate this in the Cartesian coordinates. Okay? So if I do this, I'm going to do basically the way I did. So let me draw an arrow lines in the y-axis because I wanted to integrate it with respect to y first. All right? Yeah. So then what do we have here? So let's write it down. Okay, so this double integral will equal, okay, two integrals. First is the y, next is x. Okay. First, for the y limits, this is what we draw. First contact is 0. Second contact is what? Okay, is this. For the x, you sweep this line across this shadow. The edge is 0 to 1. Okay, so 0, 0 to 1. Okay. That's it. So this thing needs to be a fairly simple expression. Okay, so let's calculate this double integral. This is 1/3 y cubed, 0 to 1 root square, and dx. So what do we have? This is 1/3. Let's take the 1/3 out of the integral here. Integral 0 to 1. So sub the upper limit here, and right, that's this over here. That's root and to the power 3. So that's what we have here, right? That's what we have. And 0 to here is 0. So that's it. So dx. Okay, dx. Okay, so this is basically the integral here. I think if there's this integral, probably a lot of us will get stuck at here, right? The Euro technique is to let x equal to sine u in general. So we end up with dx equal to cosine u du. Okay, if you don't want it, you don't have to write anymore, okay? But I will just illustrate how complicated it's becoming. Then, for if x equal to this, so x goes from 0 to 1, then that basically means you sub the 0 to here, you go from 0 to where? To, so when x equal to 0, u is 0. When x equal to 1, u equal to pi over 2, right? Yeah. So now your integral becomes, so for this one here, the integral is 1/3, 0 to pi over 2. And inside here is 1 minus sine u squared and 3 over 2. And dx is cosine u du. Right? Yeah. Okay. So 1 minus sine u squared, which is close. Yeah. It is or not. I write the hint in the exam, but lots of people didn't use that. So cosine u squared, 3 over 2. So what does this give you? Cosine squared to the power of 3 over 2. So a squared to the power of 3 over 2 equal a root 2? No. Cube, right? Cosine cube. Cosine cube times cosine u. Cosine u to the power of 4 du. Okay, that looks pretty simple. Actually, it's not as simple as it looks. So you will need to apply a formula. You know, if you do this, then the next step is to apply the integral by parts. If you manually do this, so otherwise, okay, yeah. Otherwise, you do have a formula for this. Okay. Yeah. So this is basically a little bit out of touch. You know, as engineers, generally we don't really care about how this is calculated. You can look up the formula to get this. That's fine. Yeah, right. But it's a different story though, huh? If you have a very simple substitution or integral by parts, that you have to be able to do it. So anyway, you have a general formula. This is 4 here. The n here equal to 4. You can apply the formula to calculate this. Okay. Yeah. But, you know, I don't want you to calculate this though. All I'm trying to show you here is, you see, sticking with the Cartesian coordinates is actually, you know, you can do it, but it's just so complicated, right? Yeah. This is why we bring up the next topic is we can also evaluate the double integral like this using the so-called polar coordinates. All right? Yeah. And you will see that I use the same example. You will see that it's much easier, you know, to calculate, to evaluate this double integral. All right? Yeah. So let me start the Cartesian, the polar coordinate, then we can call it a day here. Okay? Polar coordinates. So what is polar coordinates? Okay? You need to understand is, it doesn't matter the name, you know, whether Cartesian, polar. In the future, there's also spherical coordinates, okay, or cylindrical coordinates. It's all about the way, you know, different ways of describing the location in the 3D space, right? And that's a coordinate system, basically. And this is a Cartesian coordinates. If I have a point in the 3D space, okay, so the other way of describing this this location of the 3D space is using what? Using the distance from origin to that point and the angle between this vector and the x-axis. Okay, so basically you can also use r theta, okay, for this point P. Okay, for point P. So instead of using x and y, you can also use r theta for the point for the point P. So you see, if x is 1, 1, right? If x is 1, 1, what's r theta? R will be root 2. Theta would be pi over 2, or pi over 4, right? Yeah. So that refers to the same location. What's the connection then between this r theta here is what we call polar coordinates. Okay, polar coordinates. And what is the connection between the polar and the Cartesian? It's very simple. Here's x and here's y. So in terms of, if I express x in terms of r and theta, which is what? R cos theta. Yeah, r sin theta. Okay? So this is the connection basically between the polar and the Cartesian coordinates, right? So now the next question is, I said I don't want, basically if I have this double integral, and I don't want to evaluate this double integral in Cartesian coordinate anymore. I want to evaluate it using polar. Basically, I don't want x, y anymore. I want everything in terms of the r and theta, right? So one simple thing you can do is, you see this is a function f of x, y. So the function f of x, y can be simply changed to what? F of the x, instead of x, you change that to r cos theta. And the y, you change that to r sine theta, right? So that's as simple as that. You can change that f of x, y using this connection in here. Then you get rid of the x and y, everything in terms of r and theta now. However, the trick is this dA here. What's the dA? dA is dx dy, right? It's in the Cartesian coordinates. How do we change the dx dy into something like a dr d theta? So it's not going to be a straightforward change, just one like this. There's actually going to be something before here. Okay, so the question is, what will be this? And we can talk about it in the next lecture. Okay? Yeah. Any questions? All good?